This is lesson 3.6, factoring polynomials. It's going to be split into two videos. The first video is on something called the remainder theorem, and the second video will be on the factor theorem. In order to describe what the remainder theorem is, we must first do some polynomial division so we can explore further the remainder theorem. So let's warm up by doing a little bit of polynomial division. We're going to take our function f of x and divide it by the binomial x minus 1. And we'll do it by doing polynomial division or long division, not synthetic. So we'll take our x minus 1 and we're going to divide that into 3x squared minus 5x plus 4. And to start, we know we can't divide two terms into one term, so we're going to move straight to our second term, and we're going to divide 3x squared minus 5x by x minus 1. And we can do that by asking ourselves what times x gives us 3x squared, and the answer is 3x. 3x times x gives us our 3x squared, and we're always building to that first term. 3x times negative 1 is negative 3x. And then we subtract down the columns. 3x squared minus 3x squared is 0. Negative 5x minus negative 3x is like negative 5x plus 3x, which is negative 2x. Bring down the plus 4, and now we're going to divide negative 2x plus 4 by x minus 1, and we can do that by asking ourselves what times x gives us negative 2x, and the answer is of course negative 2. Negative 2 times x is negative 2x. And follow it through, negative 2 times negative 1 is positive 2, and then subtract down the columns. Negative 2 minus negative 2 is 0, 4 subtract 2 is 2. So we have a remainder of 2. Therefore, we can write a division statement and say that our binomial x minus 1 times our answer 3x minus 2 plus our remainder of 2 will equal the original polynomial 3x squared minus 5x plus 4. And there is a restriction on this. Since we're taking a polynomial and dividing by x minus 1, we know we can't divide by 0, and the number that would make x minus 1 equal 0 is 1 for x. 1 minus 1 would be 0. And since we can't divide by 0, we would have to say that x cannot equal 1. So the question that the remainder theorem asks is there a way to determine the remainder without doing long division? And there is. So I'm going to show you first what the strategy is, and then we'll make a comparison and we'll conclude why it works. So if x minus 1 is of the form x minus k, then k would be 1. And the question here is, what does the function equal at 1? If we plug in 1, what's our function equal? Well, the function at 1 would be 3 times x squared, or 1 squared, minus 5 times x plus 4. That's the original function. And we're plugging in 1. 1 squared is 1 times 3 is 3. Minus 5 times 1 is minus 5 plus 4. 3 subtract 5 is negative 2 plus 4 is 2. The function at 1 is 2. Now you might see some similarities here between our answer 2 and our remainder from our polynomial division. And that is essentially what the remainder theorem is. It says that if you take your k value from the term you're dividing your polynomial by, in this case x minus 1, our k would be 1, and you substitute 1 into the equation, you're left with just the remainder. Why does that work? Well, the reason it works is if we go look at our division statement, what would happen if we plugged 1 into this division statement? Well, 1 minus 1 is 0, and 0 times anything is 0. We're just left with plus 2. And that's the remainder theorem. What we notice about the above result and our original remainder is that they are in fact the same thing. And what the remainder theorem states is that when a polynomial, f of x, is divided by x minus a, the remainder is just the function at a. So whatever that minus a is, whatever that a is, if we plug that into the original function, our answer is the remainder. And that's the remainder theorem. We can practice on the next page. If we were asked to determine the remainder when our polynomial is divided by x plus 7, we can find the remainder by naming this a function. Let's call it g of x. And then just determining what our k would be. In this case, k would be negative 7, because that's the value that would make that bracket 0. So if we want the remainder, we would take our function and set it equal to negative 7. So that would be negative 7 cubed plus 7 times negative 7 squared plus 2 times negative 7 minus 5. And if we plug that directly into our calculator, we should be able to come to a single number, and that single number answer is negative 19. And if we were to do the division, we should come up with negative 19 as a remainder. And we could check that by doing synthetic division. So let's try. In synthetic division, or polynomial division, we could do polynomial division, long division, but let's try synthetic. We'll take our k value, negative 7, and we'll take our coefficients, 1, 7, 2, negative 5, from our polynomial, 1, 7, 2, negative 5. And we'll do some synthetic. Bring down the 1, multiply, we get negative 7, add down the column, we get 0, multiply, we get 0, add down the column, we have 2, multiply, we get negative 14, add down the column, negative 19. The last term is always the remainder is negative 19. So we can come up with the remainder by taking our k, or whatever value would make that divisor 0, whatever x value would make that divisor 0, plug it into your function and solve. We get negative 19. Synthetic division confirms that the remainder is indeed negative 19. That's the remainder theorem. There's one example here that I'll get you to try on your own. We're going to do a similar question as a warm-up tomorrow. So if you have difficulty with this question, we'll look again at it tomorrow, but try it. It's a different little spin on the remainder theorem. Instead of asking you to find the remainder, I'm giving you the remainder to start, and I'm asking you to find one of the coefficients from the original polynomial. See if you can use this idea of the function at our k value equal to the remainder to solve for k. And if you can, great, and if you can't, we'll look further at it tomorrow. That's it for the remainder theorem. Thanks for watching, and be sure to watch the second video, the factor theorem.